Welcome everybody back to day 3 of the Python Web Conference 2020. I'm really excited. I've got Gareth Greenway with me here today, and he's going to be talking about all the right buzzwords, Kubernetes clusters, and Salt Stack. So I will let him take it away.
All right, thank you, Calvin. So yeah, as Calvin said, I'm going to be speaking about Kubernetes clusters and Salt. Just to give a little background on me, my name is Gareth Greenway. I live and work in Southern California. I work for the company SaltStack, where I'm a senior software engineer. I'm one of the fortunate few, more and more these days, that get to spend my days working on open source software. So if you have the opportunity, I highly recommend it. And I've included my GitHub and my Twitter accounts there, if anyone feels like tweeting at me or about me during the talk. In a previous life, I was part of a team that started and ran an in-person conference in Southern California with a free and open source theme to it. Because of my involvements in running that conference for almost 15 years, I have a unique understanding of what goes into running a conference, the logistics of behind the scenes. I can't even imagine the logistics that have gone into running a virtual conference like this. As I was just saying to Calvin beforehand, we were chatting. My experience so far has been, this has been one of the best virtual conferences that I've seen or participated in. So if you haven't already, please thank Calvin and Mary Beth and the rest of the organizers. They've done a phenomenal job. So again, this is Kubernetes clusters with Salt. So just a quick agenda of stuff that we'll go over. So we'll do a quick introduction to Salt. I'm going to probably use the terms interchangeably, Salt and Salt Stack. Salt Stack is the company, Salt is the project, but it's often referred to as Salt Stack or Salt. So we'll also do a brief introduction to Kubernetes and a project called K3S. We'll look at installing and setting up Kubernetes, which will be actually K3S via Salt. Then we'll look at controlling Kubernetes via Salt and why we would want to do this. And then we'll look at bringing events from Kubernetes, K3S, and Docker into Salt and why we might want to do that. We'll also look at writing some custom Salt modules. And then finally, if there's time available, I will show a quick demo, depending on how much time we have, of a Kubernetes cluster running and be controlled by Salt. So a couple Salt basics. Before we begin, I wanted to kind of go over some terminology, some terms that I'm going to use, some concepts, just so we're familiar with the concepts of Salt and Salt Stack. So Salt is written in pure Python, completely Python. It's completely open source. And it's currently what I like to refer to as a DevOps platform, with many of its functions, such as remote execution and configuration management, filling a similar space to some other tools that people may have heard of, such as Chef, Puppet, Ansible, or Pulumi. So Salt originally began as a remote execution system. So basically a way to execute the same command across multiple machines. So similar in nature to some older tools such as Fabric or Funk, but not done over SSH. So everything that Salt does is encrypted, and it's done using the 0MQ messaging bus. So it's very fast in its operations. And because of the way it was designed, adding additional components such as configuration management through the state modules was really, really easy. And everything that Salt does is done using the same Salt API, which is easily exposed to other purposes, and additionally reusing a lot of Salt components, which we'll look at a bit later. So some of the Salt components that we're going to look at today include the Salt event bus. So this is the heart of Salt Stack, and really what allows all the pieces to fit together. And it's the magic, the secret sauce of Salt. So we also have state modules, and these are used for configuration management. So the idea is that they set your machines, your instances, your hosts into the desired state. And they're only executed if and when they need to make changes. We also have execution modules. Remote execution modules is sometimes the term that's used. And so these are really the heavy lifters of Salt Stack. So these are the ones that are doing all the work. These are the ones that are installing packages. These are the ones that are setting opening files, setting contents of files. And they are used by just about every other component within Salt, including the state modules. So we also have reactors. So reactors are small Salt modules that wait for specific events and react in some manner, running a specific module or state. And we'll look at some of those a bit later. And we also have pillar data, which is secure data stored on the Salt master, providing targeted access to secrets and passwords for Salt minions, similar to things like Puppet's Hiera system or Chef's Ojai system. Excuse me.
Hey, Gareth,
Yes.
We're still seeing your title slide.
Oh.
Or it's like the Google slide itself, like the interface.
Okay.
You must have shared, maybe we had it playing on the screen. I just saw it briefly.
Let me try again. Can you see the right screen now?
No, I'm seeing your presenter notes now, like the UI of slides.
Okay. How's that look?
Bingo.
Bingo, there we go. Okay. All right, so yeah, all right. So within Salt, devices that are controlled by Salt are commonly known as Salt minions. And each device will be running a piece of software called the Salt minion. So the Salt minion is a daemon that receives commands from a remote Salt master via the Salt event bus. And the device or server, which within the environment that controls the Salt minions, is known as the Salt master. This device is running a piece of software aptly named the Salt-master. And the Salt master daemon sends commands to the Salt minions via the Salt event bus. So a typical Salt setup indicates a single Salt master, includes a single Salt master, controlling many minions. We can also have a setup with multiple masters controlling many minions. And we also have the option to run what's known as masterless mode with only minions in place. So as I said, the Salt event bus is the heart of Salt Stack and distinguishes Salt from a lot of similar projects in the same space. So the Salt master and the Salt minion each have their own event buses. The event bus is used by the Salt master to publish commands to all Salt minions, and then by the Salt minion to publish the return information for a job back to the Salt master. The Salt minion uses its own local event bus for locally run commands that need to interact with the running Salt minion. So here we have a diagram kind of illustrating what the Salt event bus looks like and all the various components that plug into it. So the middle line down the middle we have is labeled the Salt bus or the Salt event bus. And we have minions running a variety of operating systems, including Windows, Linux, AIX, and some of the network devices such as routers and switches. At the master level, we can see the various components such as runners, reactors, engines, and the Salt API. We can also see that the Salt master is providing things like Pillar, the file server for providing state files, and handling minion authentication. And we'll look at ways that we can use the Salt event bus a bit later. So within Salt, we have a concept called targeting. So targeting is the way one specifies which minion should run a command or execute a state by matching against host names or system information, or define groups, or even a combination thereof. And we have a variety of different ways that we can target. So the most common way is using globbing or targeting using the minion ID. So globbing allows targeting of many minions using a part of the minion ID. In these three examples, first, we're targeting all the minions that the Salt master knows about. Second, we're targeting all minions, or any minion whose minion ID begins with the word minion. And then third, we're targeting a single minion. We can also target based on grains values. So grains are system information. So like what operating system it's running, what IP address it's running, what IP address it's using on a particular interface. So in this case, we're targeting a minion whose OS grain is Fedora. So this would target any machine that the Salt master knows about that is running the Fedora operating system. And then finally, we can combine targeting using compound targeting. In this example, we're targeting all minions whose OS grain is Debian and whose minion ID begins with WebServe. So here we have an example of targeting all the machines that the Salt master knows about using the asterisk or glob. In this example, there are many machines on that our Saltmaster knows about running Linux, Solaris, FreeBSD, Windows, and OS X. And they're receiving the same command from the Saltmaster, the usage function in the disk module. Because of the way Salt modules are designed, there may be separate modules handling the various functions based on the operating system in question. For example, we could have different modules handling disk functions for each of these operating systems. But by using a concept called virtual functions, they would each appear to the minion as the Saltmaster disk. This allows us to run target the same command against all minions and have Salt figure out the right one to use. So Kubernetes. Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services. Just a quick disclaimer, I am not, nor do I claim to be a Kubernetes expert. I'm a casual user at best. Like many other people, I built a Raspberry Pi Kubernetes cluster to show how Salt works with Kubernetes. This led to my interest in casually playing and learning Kubernetes. And there was a really great talk yesterday by Angel Rivera that went into a lot more details about the topic of Kubernetes. So if you're interested in more details about Kubernetes, I highly recommend that you check out that talk. So just a couple Kubernetes terms that we're going to be using that I'm going to mention during these talks. And as I said, I'm not an expert. So if I got some of these wrong, that is why. But please point out in Slack so that I can prove this talk. So containers. Containers are the most common way to run applications within a Kubernetes Docker cluster using container technology such as Docker or Containerd. We also have pods, and pods are containers that will be running across the cluster. So within a Kubernetes cluster, the nodes are the individual machines or instances where the pods are running. We also have services, and that's how pods are accessible. It's a logical set of pods and a policy of how those pods will be accessed. There's also a deployment, which is a collection of pods and how many replicate sets the pod should have of that pod. And then a replica set is the number of replicas of a particular pod that should be running in the cluster. We also have context, which is a group of access parameters. So each context contains a Kubernetes cluster, a username, and a namespace. And finally, we have namespaces, which are, think of them as virtual clusters within Kubernetes. So Kubernetes starts with 4 initial namespaces, but you're welcome to and able to add additional ones as you see fit. So we're going to be looking specifically at a project called K3S for a lot of the examples today. K3S is a very lightweight version of Kubernetes. In Angel's talk yesterday, he mentioned that like oftentimes Kubernetes refer to K8s or K8s, and that's because of the space, the number of letters between the K and the S. K3S kind of plays on that a little bit. They took the 3 most commonly used components of Kubernetes, and then kind of threw away the other 5, and then they reached K3S. So K3S is highly optimized for ARM, which makes it really good for running on Raspberry Pi clusters, both ARM64 and ARM v7. It works really well on Raspberry Pis. It's also a lot more lighter. So if you just want to run it on your laptop or like a single machine just to play around with, it's a really good project. And it's really easily installable via a download script, which we'll take a look at in a second. So we're going to look at installing Kubernetes via Salt. And just a caveat, this is installing K3S with Salt. There are some really good Salt formulas. So Salt formulas are collections of Salt states that have been put together by the Salt community, available via GitHub. So if you go to GitHub, Salt formulas, I think it is, under the SaltStack project or account, there's some really good formulas on setting up Kubernetes, like the full Kubernetes. But we're going to look at installing K3S. So here we have a simple, what we refer to as a Salt state. So to install Kubernetes on a node that's going to be our control node, we'll use the following state. So in this case, we're taking advantage of the script function within the CMD state module. And the script function is specifically designed to download a script from a remote server and run it with any passed arguments. So we can see here that we're setting up some environmental variables to pass along to the K3s install script. So here we're telling it to run the -- Docker flag, so that it uses Docker for its container. By default, it will use container D, but we want to use Docker, and we'll see why a little bit later. So we're also telling it we want to run a specific version of K3s on our cluster. If you didn't provide this environmental variable, it will install the latest. I'm just running this version because I had run into some issues with interacting with various components. So I've locked it to the specific version. This would be a good way if you wanted to downgrade to a specific version or upgrade to a version that you wanted to make sure that you were using. One thing I wanted to point out in the state file, as with any state file that you're using within Salt, the top line, which we have here, install_K3s_server, is known as the ID or the name of the state. And it needs to be unique across any states that you're running. So if I had multiple definitions here, each state within a state file needs a different, a unique name. So once the state has finished running, assuming everything worked as expected, we can run the kubectl command on our control node and say that we have a single node in our cluster with the role of master. So once we set up our Kubernetes node, we'll take a look at the salt mine. The salt mine is used to collect arbitrary data from the minions and stored on the master. This data is then made available to minions via the mine module. By default, the salt mine on the minion will refresh the data every 60 minutes. So this is going to be the mine configuration that we're going to use for our K3s control node. So here we're defining 3 mine items from the control node that we want to be made available on the master for our other salt minions to use. We've included the test.ping as a test to ensure that the mine is working. The test.ping function will simply go out to the minion node and then return true, assuming that communication is working. Otherwise, it will return false. So it's a good test to ensure that the salt mine is working as expected. We're also including the IP address of the ETH0 interface and the contents of rlib rancher K3s server node -token in Kubernetes IP and Kubernetes token respectively. And we'll see why we're pulling those out when we set up our agent nodes. So here we have the salt state file that we'll push out to the mine.conf file in our K3s control node. We're using the file.manage function and giving it a salt file server path where our file lives. Because this is a salt minion configuration, we want to ensure that our salt minion is restarted so that the new configuration is applied and our salt minion is updated. Here we're using the command.run function to call the command service restart saltminion.service in the event that there are any changes to the file etc saltminion.d-conf. We're using this command we're having this command on the run in the background so that our salt call isn't waiting for the return while the salt minion restarts. So to install K3s on the machines that will be our Kubernetes agent nodes, we're using the following state file. It should look very similar to the last state file that we used to install the control node. At the top of this particular state file, we're using some Jinja templating to query the salt mine for the values that we had previously set up to be available from the K3s control node. We set these values into variables called Kubernetes token and Kubernetes IP respectively. Again, we're taking advantage of the script function within the command state module and calling the same script that we used before to install the K3s control node. This time we're including some additional environmental variables. We're still including the version that we want to use, and we want to ensure we're setting up K3s to use Docker. We're also including a variable for the K3s URL and the K3s token. This will tell the install script that this will be an agent node and that the IP of our K3s control node should be this server. We're also providing the token that was generated when K3s was installed on our control node. We're also including some additional variables for the version of K3s we want to install, making it easier to upgrade or downgrade later. So once that salt state has finished running and assuming everything worked as expected, we can run the kubectl command on our control node and see that our agents are up and running and have checked in with the control node and are ready to start running some pods. For additional information for our pods, we could also include the -o wide option to kubectl and see information such as IP addresses, operating systems, container runtime, and kernel versions of our nodes. So next we'll look at in controlling a Kubernetes cluster using Salt. So one question that people might be asking themselves is why would we want to do this since Kubernetes already has its own management tools? And there's a number of reasons why we might want to use something like Salt to manage our Kubernetes cluster or clusters. First is the concept of infrastructure as code. This is the definition of infrastructure as code according to Wikipedia, which I'm not going to be reading verbatim, but wanted to include. As we've heard in a lot of sessions at this and other conferences, the concept of infrastructure as code is gaining a lot of momentum and attention. It's not necessarily a new concept. Lots of DevOps engineers and system administrators have been writing little one-off scripts and processes to make their jobs easier for years. But we're seeing adding things like version control. We're seeing things like version control being introduced, testing of these processes and scripts, and seeing these scripts being adapted into more formal configuration management systems, such as Salt. So that makes them easier to read, understand, and maintain. So adding in more processes and bringing in the concepts that have been working for software development into the system management side. So reusability is important. If we've taken the time and put in the effort to automate something that's installing and maintaining our cluster, we want to be able to reuse that automation in the form of templates. So building on that, we could be maintaining multiple clusters, a dev cluster, a QA cluster, and a production cluster. It would be nice to be able to manage all of them with the same infrastructure code simply by flipping a few variable values. We'd also be managing multiple clusters across multiple servers or data centers. We'd like to avoid having to manually log into those servers to run commands. And finally, repeatability. As we saw when installing Kubernetes or K3S in this case, being able to install or reinstall Kubernetes can be very helpful. We can envision a scenario where a week, a month, a year after something has been installed manually, and being in a situation where it needs to be reinstalled. Remembering all the steps could be quite challenging. Much the same, needing to recreate a Kubernetes cluster after some time, which was previously created manually, and trying to remember the commands or searching the shell history for what was run would definitely not be fun. Being able to create and recreate our Kubernetes clusters easily in a repeatable fashion can also be very helpful. So in order to control a Kubernetes cluster from a Salt master, we need to ensure that some additional pieces are installed and configured on the Kubernetes control node, specifically the Python Kubernetes library. Here we're using the pkg.installed function to ensure that Python 3-pip is installed and that we get access to pip. We can then use the pip.installed function to ensure that the Kubernetes Python library is installed. In my testing, I had some issues using versions higher than 11.0.0.b2. So in this case, I'm locking it to a specific version. So we also want to make sure that pip is installed before installing it. So we include a require on the package state that is installing Python 3-pip. We also need to point the Salt minion on our control node to the configuration file that contains all of our Kubernetes configuration options, such as what server to use, the username, passwords, tokens, etc. We'll also need to specify what the context is. In previous versions of Salt, we needed to specify these values individually in a Salt configuration file. Now we simply point Salt at the file that is created when we install and set up Kubernetes or K3S. As we created a similar state to what we previously had, we created a new salt state to ensure that the file for the Kubernetes configuration is in place. And we also ensure that the Salt minion running on our control node is restarted if and when that file changes, so that the new configuration takes place. We can also combine them into a single file. So here we have the file managing our mine as well as our Kubernetes configuration with a single restart watching both files. Once the configuration is in place and the salt minion on our control node has been restarted, we can then target our control node from the salt master and use the salt Kubernetes module to query our cluster. Here we can see all the nodes that are active in our cluster. We can gather information from the cluster as well. Here we see all the namespaces that are currently configured. So we have default, kube system, kube public, kube node, and release. And these are all the default namespaces. And we can also query information about a particular node, particular namespace. In this case, we're looking at the running pods in the kube system namespace. We can also query some information about an individual node. This command produces a lot of Kubernetes information about the node, including general information such as operating system. It also includes information about the Kubernetes configuration on the node, as well as any container images that are available, as well as the status of the node, including things like capacity. Because of the breadth of information that this command returns, I've condensed it quite a bit for this slide. So one of the things that we can take advantage of now that Salt is able to control our Kubernetes cluster is being able to deploy containers to the running Kubernetes cluster. So here we have we're using the deployment underscore present function in Kubernetes, in a Kubernetes state module to create a deployment of Nginx containers. When we run this state file, the deployment will be created with 12 replicas of our Nginx container. They'll all receive the label my-nginx that can be later used when adding them to a Kubernetes service. Here we've updated the state file to use some Jinja templating for the number of replicas that we want in a cluster. And each time the state file runs, a random number generated between 2 and 24 will be used for the number of replicas. Our deployment will be replaced with a new one with this amount of replicas in place each time the state file is run. And of course, we'll want to delete deployments in the cluster. So we can do that with the deployment underscore absent function in the Kubernetes state module. Here we're specifying the number of deployments or the name of the deployment that we want to delete and specifying a propagation policy of background, which will delete any objects in the background. By default, the orphan policy will be used, so various objects such as pods and replica sets from the deployment will just be abandoned. So we'll also want to be able to deploy services so that our containers are accessible. For that, we'll use the service underscore present in the Kubernetes state module. And here we're showing that we can specify an existing YAML file of Kubernetes commands or a Kubernetes YAML file passed along to the service present for setting up the components within Kubernetes. So Docker events and Salt. When we installed K3s on our Kubernetes cluster, we specified that we wanted the containers within the cluster to be running Docker because we wanted to be able to take advantage of events that are generated by the Docker system. So within Salt, we have a component called events or called engines. Engines are long-running processes that connect to external programs and services, feeding information to Salt. Such examples of engines that ship with Salt today include SQS engine for pulling in data from Amazon's SQS server, the Logstash engine for pulling in data from Logstash, the Slack engine for controlling Salt via Slack, and the Docker engine for bringing information into Salt from Docker. So placing this configuration on each of the Kubernetes agent nodes with the following state file. Here we're configuring two engines, one called Docker underscore events that will listen to the local Unix socket for any events from the Docker daemon. We've also included one called blinkt that we'll talk a bit more later. So we also need to ensure that the Python 3 Docker library is installed on each of our minions to make sure that we can take advantage of Docker events. So we use this state file. So here we're ensuring that the engines configuration is in place. We use the package.installed state function to install Python 3 Docker, and then we go ahead and restart the Salt minion if the engines.conf has changed. So here's an example of an event that we might see on the Salt event bus when a Docker container has been started. zooming in a little bit on the details, we can see that the event tag is salt engine docker _ events /salt/state. And we have the ID of the minion where this event originated. We would also see similar events for when a Docker container is destroyed, created, stopped, when volumes are mounted. There's quite a lot of events that Docker pumps out. So the next thing we want to look at is reactors. So as I said, reactors give Salt the ability to trigger actions in response to an event. It's a simple interface watching Salt's event bus for event tags that match a given pattern and then running one or more commands in response. The system binds SLS files or state files to event tags on the master. Those state files then define reactions. This means that the reactor system has two parts. First, the reactor option needs to be set in the master configuration, and then the reactor option the reactor option allows for event tags to be associated with a reactor file. And then second, the reactor files use high data, such as the state system, to define reactions to be executed. So we have a couple different reactions that are available for us to set up. So we have local reactors, which are reactions that carry any of the available remote execution functions on the targeted minion or minions. We also have runner reactions. So these are reactions that execute a runner function directly on the master. We also have wheel reactions. And these are reactions that execute a wheel function on the master. So some of these include type of reactions would be when a minion key is removed, when an AWS instance has been removed, or when a minion authenticates against the master on its first kind of startup. We also have caller reactions, which are commonly used in masterless mode. So on our Salt master, we wanted to find some reactions for the 4 Docker events: destroy, stop, create, and start. When the Salt master sees one of these events on the event bus, it will run the respective reactor files. By default, the Salt state files are typically written in YAML with some Jinja templating. But for more complicated needs, there's the option to write state files in pure Python. Any state file that is written in Python needs to have a run function. This is what Salt looks for when running this particular state. In this particular example, we're defining a simple dictionary called kwargs with the start and end values, some color values, and a timeout. We'll look at what these are for in a bit. Finally, we're defining a state as a combination of a dictionary with a unique ID of Docker destroy. Within the state, this will be a local reactor, so the function will be run on a minion. We're then telling the local reactor that we want to run range _ RGB function. We're passing a list of dictionaries along to the local reactor call. Each dictionary contains a single key. The first key is the target minion, where we want the execution module to run, and the second is the keyword arguments we want to pass along to the execution module. We're then returning the contents of the state, which will be what is returned from the call. So the next thing we want to look at is custom modules. So one of the powerful things about Salt is how easy it is to enhance and extend its functionality. Most of the components including many of those that we've looked at so far, can be added to with custom modules. So as I mentioned before, I was inspired by various blog posts on people building Kubernetes clusters from Raspberry Pis. So I wanted to give it a try. And I also wanted to be able to use it with Salt and show how Salt could interact with Kubernetes and Docker events. So using a small little GPIO board called the Blink-T board sold by Adafruit on the Raspberry Pi provided this solution. Each board has 8 individually addressable LEDs, and as a bonus, there was an existing Python library available for interacting with the board. So I wrote a little custom Salt module to interact with the board using this Python library. And here's the code for that module. So a couple things to point out. in the module. So we're setting a virtual name of Blink T, and we're doing this as we need to. We're doing this because we're also importing the Blink T Python library, and when we place this in on our salt minions, where it's going to be located, there would be a conflict between the Python library and our module. And so by naming it a virtual name of Blink T, we name our file blinkt_mod to avoid those conflicts. So we're doing a try except when attempting to load the Blink T module. If the Blink T module is successfully loaded, then we set Blink T as true. If it fails, then we set it as false. We then use this value, the value of has Blink T, inside the dunder virtual function to determine if the Blink T module should be available on our salt minion. If the value is true, then we return the virtual name. Otherwise, we return false and a message saying why we're returning false. And the rest of the module includes the function that we were calling before in the reactor. And the accepted values should look similar. So an interesting thing to point out in this execution module is that we're making a call to the fire function in the event module to fire an event onto the local minion event bus with the arguments, with the name of the arguments that were and the name of the function that was called. We then have a custom engine that's listening for these events, handling and then turning on the specific lights to the specified colors. And this is that engine. So again, we're doing similar things that we were in the module. We have the try except and the virtual function. And we're using a class in this case, just called blinkt engine, which defines a run function. And then we're using the similar function that we saw in the module to listen to the event bus. So we're using salt utils event get master or get event, depending on if we're running on the master or the minion. Whoops. And so then we just loop, listening for the event bus for a specific tag that starts with salt minion blink T, and then running the particular function within here that we want to do. In this case, range RGB. And there's our range RGB function. So it takes all the arguments previously passed to turn on. And the reason I did it this way, using the module and engine, just in case anyone was curious, is I wanted to be able to have something running that would turn on the individual LEDs and then leave them on for a specified time, like 5 seconds, 10 seconds, and then turn them off. And so the way that salt modules usually work is once they've run a command, that's it, they're done, they return. And so using an engine, I was able to have something constantly polling, waiting to turn them off. So side note. And then every engine that we have requires a start function, similar to the state files written in Python, where salt looks for the run function. Salt will look for an engine, a start function within an engine, and that's how it knows, like, this is where I look to start up this engine. So once we have our blinkt module and our blinkt engine, if we place these on our salt master in the directories srv salt _modules and srv salt _engines, and then target all of our minions, running the command saltutil.sync all, we will see a similar output to this on all the minions, and we can see that it is synced over the engines.blinkt as well as the modules.blinktmod. So I'm going to I think we have a couple minutes left, right, Calvin? 5 minutes?
Correct, you have 5 minutes left.
Okay, perfect. I'm just going to give a quick demo. Okay, so this is, I just have a simple shell here on the Kubernetes cluster. And is that coming through okay, size-wise?
Yeah, the text is a little small, but it'll work.
Okay. So I'm just going to run a couple quick commands. So let me switch over here. So I've done the kind of baking show approach to this, and I've already set this up. So we can see this is running Kubernetes. It's running Kubernetes K3s, and these are all of my minions. So this is just using the kubectl commands. But if I switch back to my my salt master here, oops, there are no pods. You can see that all the commands that I mentioned do in fact work, and we can query our Kubernetes cluster. So just switching over, let me switch my camera. Okay, so you should be seeing a shot of the Kubernetes cluster.
Correct. Yeah, we see it.
Okay. So if I run a couple commands, we should see some lights come on in a second. And these are the lights that are corresponding with, and it's a little hard to see, the camera doesn't quite focus on them. But these are red, or blue and green lights corresponding with the Kubernetes cluster just starting up 13 containers. And then if I run the absent, oops, the state, which will delete them all, and it's the timeout killed them. So there's red and purple as the containers that are destroyed. And that's all I have. I'm happy to hang out in the gallery if anyone has any questions about Salt, the cluster in general. I think we got a couple minutes, like 1 minute left if anyone has any.
Yeah, we were kind of like 1 minute right there. So if people had questions, I didn't see any questions in Slido. There are a couple comments in the Track 1 Slack, but if folks want to join you in the gallery, just click the link below here and head over to the gallery. Gareth will be there, happy to answer some questions. I love geeking out on this kind of stuff, so that's a really cool talk.
Thank you.